Welcome to the class of design of prestress concrete. Today we will discuss about deflection due to prestress. Now there are some generalized formula about the deflection due to prestress depending upon the beam cases. Okay, so here I am writing this is beam case, and here the deflection. Number one is, so this is a rectangular beam and this is the neutral axis, and assume the tendon is here. Okay, and the value of the eccentricity is E, and there is a compressive prestressing force. The value of the prestressing force is P, and if the length of the beam is L, then the deflection value we can write down as minus PEL square divided by 8 EI. Okay. Number 2, this is a rectangular beam and this is the neutral axis. Now the tendon is lying in this position. Okay, this is L1, this is L2, and total length of the beam is L, and this is the prestressing force. Then the deflection value would be minus PE by 6 EI 2 L1 square plus 6 L1 L2 plus 3 L2 square. Okay, now case number 3. In these two positions the tendons were straight line. Okay, first was straight line just below the eccentricity of E. Okay, here the eccentricity is E. Okay, and for another case, this is the rectangular beam, this is neutral axis, and the tendon is like parabolic in nature, this way. This is a P force, and the eccentricity, maximum eccentricity is E. Then deflection value will be minus PEL square by 48 EI. Okay, and number 4, this is a rectangular beam and this is the neutral axis, but the different case from here to here is the tendon is not starts from the neutral axis, it upward from the neutral axis and goes on like that. Okay, this is the compressive prestressing force P, and here eccentricity is E2 and here eccentricity is E1. There is two eccentricity in this fixture. So deflection would be PL square by 48 EI minus 5 EI E1 plus E2. Okay, and the last scenario is, this is a rectangular beam and the tendon would be triangular in nature, but the tendon profile start like follows this manner. Okay, so this is the prestressing force and the eccentricity here is E1 and eccentricity here is E2. Then the deflection value would be PL square by 24 EI into minus 2 E1 plus E2. Okay, this one and this one is very much important for your syllabus. Okay, now so these are the formula for deflection due to prestress. Now deflection due to self load or dead load we already know, that is 5W L to the power 4 by 384 EI. Okay, I have write it down. Deflection due to self weight or dead load, we all know the value is we denoted as del G. This is del P because deflection due to prestress, that is del P, and deflection due to dead load or self weight of the beam or slab, whatever you can say, that is del G, and the value is 5W L to the power 4 divided by 384 EI. Here W is the load per meter run or load per unit length. Okay, so these value formulas are very much important for solving any numerical problem on deflection due to prestress. Now we have to know deflection due to live load. Okay, and we are denoting this as del W. Here are three scenarios as well as. Number one is if there is a point load, if there is a rectangular beam and the length of the beam is W and there is a point load at the center of the beam, then your deflection due to live load would be WL cube divided by 48 EI. Okay, and in the next scenario, if there is a UDL, right, the beam nature is same but the loading condition is not a point load but UDL, and the value of the UDL is W, then del W would be nothing but as per your dead load formula, that is 384 EI. And another scenario we have to know, that is there is a rectangular beam and the length of the beam is L. Okay, this is L, and there is a two type of point load, there is W, there is W, and the length, this is A and this is from this end is also A, then del W would be WAL square 3 minus 4A by L the whole square divided by 24 EI. Okay, now if we calculate the total deflection, we have to sum up these all. That means del P, that is deflection due to prestress, del W, that is deflection due to live load, and del G, that is deflection due to dead load. Now if we calculate what is long term deflection, in case of long term deflection, deflection of prestress concrete beam is affected by creep also throughout its loading history, and the prestress force tends to increase the upward deflection due to the creep of the concrete. So we have to conclude, or we have to include concrete of the creep of the concrete as well as. So long term deflection would be, that is 5 plus 1 into del G plus del W minus F into del P. Now here there is two unknown part, that is phi. Phi is the creep coefficient, and the value of the creep coefficient is lies between 1.4 to 1.6. Okay, and F is the efficiency factor. This is efficiency factor, and efficiency factor lies between the values between 0.85 to 0.9. Okay, and as per IS 1343, our deflection limit in case of prestress concrete should be limited to span by 250. Okay, so these are the basic fundamentals we have to know for solving any kind of numerical problem on deflection due to prestress. Okay, that's all for today now. Thank you.